All right, good afternoon, everyone. Welcome to another lecture via Zoom for MENG 260. Hope everybody is doing great, okay? Happy Friday to everyone. Beautiful day. So I'm going to go over chapter 7 and chapter 12, and then I have example problems, as I promised you to go over example problems and clarify everything. Before I go over example problems, I just wanted to review chapter 7, some important, portion of chapter 7. There's so much stuff, information given on chapter 7, but I'm going to summarize it for you, okay? All right, so we start with the energy balance, which is for one, we assume that we have one inlet, one exit control volume, okay? One inlet, one exit control volume at a steady states. So we have the amount of heat transfer over temperature, which is also in terms of entropy which accompany the heat transfer is written as Q dot over T. J is a subscript in case we have other type of energy transfer, okay? So, and then we have the change in entropy here. And this term here, we call it the production of entropy production, okay, rate, entropy production rate. That's how it's defined. All right, so there will be, I think I posted the homework number 5 for chapter 7 and chapter 12. I was careful to assign homework that is going to be efficient for you, and you will learn a lot. Overall concept of chapter 7. Chapter 12, there are more stuff to cover, but I just gave you 2 or 3 problems for time being. If we rearrange this, and also we talk about the change in entropy here and divide everything by m dot, okay? Divide every term by m dot. So the change in entropy is S2 minus S1, 1 over m dot, as if we factor that for this part here. And then for entropy production, the rate of entropy production is given by sigma dot for control volume, okay, over m dot. A special case, if no entropy transfer accompanied by heat transfer, okay? If there is no entropy transfer accompanied by heat transfer, then this part, this term will go to 0, and all we have is a rate of entropy production is equal to change in entropy, okay? So the second law requires that, okay? This is very important, okay? Just pay attention. The second law requires that entropy production should be positive or 0, okay? The second law said that when you do the analysis, even I gave you on the homework, and I'm going to go over example problem. So if we are dealing with production of entropy, the second law requires that the entropy production, which this is called the entropy production over the mass flow rate, is positive or 0. So sigma, which is just the entropy production, if it's greater than 0, is irreversibility is present within the system, okay? Irreversibility. Opposite of irreversibility is reversible, okay? If sigma equals 0, then no irreversibility present within the system, okay? So we get either positive or 0, no negative. But, however, the change in entropy of the system may be positive, negative, or 0. The change in entropy could be, for the system, could be positive, negative, or 0. Like other properties, like enthalpy, specific volume, internal energy, entropy change can be determined without knowledge of the details of the process, okay? So, and we can use ideal gas law if we have air or gas, which we consider to be ideal gas. Using ideal gas condition, and then we can calculate the delta S. that way. But if it's a fluid, water, then we have to use table. Okay, make sure that you don't mix these two things up. All right, so this is the change in entropy. Okay, that's an entropy change, S2 minus S1, integral of change or entropy transfer accompanied by heat transfer. So that is the integrals of del Q over temperature. In some situation, this is zero, okay, zero. So plus sigma, sigma is entropy production. The direction of entropy transfer is the same as the direction of heat transfer. Note that when there is no heat transfer, there is no entropy transfer, okay? When there is no heat transfer, there is no entropy transfer. That is just a summary first part. And using the ideal gas, okay? I just wanted to refresh your memory about the ideal gas law or ideal gas model for entropy. And when you go to a table, there you will see that S with a circle on top, which is a function of temperature. And that S with a circle on top, you will see it on the table, okay? Table. It denotes the specific entropy, that's a specific entropy, at temperature T, and the pressure of 1 atmosphere. That's a condition for this entropy here. And so the condition is that it has its function of temperature and a pressure of 1 atmosphere. But when you go to the table, T-9, you only need a temperature to determine for T1, for example, you get a specific entropy 1. And then for T2, temperature 2, you get the specific entropy 2. All right, so, and the unit is kilojoules per kilogram Kelvin, okay? This property here, or entropy property, is from, it has a unit of kilojoules over kilogram Kelvin. We don't say degree Kelvin, okay? It's a scale Kelvin. All right, so Celsius plus 273 is can be converted to Kelvin. So for a gas model, the difference between a specific entropy as a function of temperature, it's minus R, which is a gas constant, natural log of P2. If pressure is given, then you use this formula here, okay? The ratio, the pressure ratio. And R, you know how to calculate the R. R is R bar over molecular weight, okay? Capital M, molecular weight for that substance. Okay, great. So another, is specific, if the assumption of constant specific heat, if you have that assumption, constant specific heat, then we have the CP, specifically a constant pressure, natural log of T1 over T2, okay, T2, minus R, natural log of P2. Let me see, no, this is a T2 and this is a T1, okay, T2 over T1, minus R, natural log of P2 over P1. So that is one formula. And if it's an open system, that is a CP is more likely to use CP instead of CV for closed system. CV, natural log of T2 over T1, plus R, natural log of a specific ratio of a specific volume, V2 over V1. So these are the two formulas you will be using in problem solving and maybe on the exams, okay? All right, so. Then mechanical energy equations, I already went over this, I'm just summarizing it. We have an energy balance. It's going to also simplify. When we simplify this equation, it's going to end up to be Bernoulli equations, okay? Mechanical energy equation. Pressure over gamma. Gamma is a specific weight and for the substance. So, and the unit is Newton per cubic meters, okay? A specific weight is equal to the density of that substance times the gravitational acceleration, so rho g. And if the pressure, the term one, we call it the pressure head, That's a pressure head. And the unit of pressure is Pascal or Newton per meter square. Specific weight as a unit of Newton per cubic meters. And if we simplify this, we end up with a meter square. Numerator is Newton per meter square. Take the reciprocal of the denominator, you get the cubic meter divided by Newton. Newton and Newton cancel each other out. And then we get meter cube over meter square. We have 1 more meters left, which is this. So therefore, each term on this mechanical energy equation, it has a unit of length, okay? Length unit. So it could be meters or inches and so on, or centimeters. So P1 over gamma, we call it the pressure head. And this is the velocity head or kinetic energy, or we call it velocity head. This formula is very useful, okay? So there is a little bit of, adjustment from the original equation because we are dividing everything by gamma, okay? By gamma, which is gamma equals rho g, so that you can unroll. Rho is also 1 over a specific volume, okay? So Z, okay, the term Z, we call it the elevation head, okay? Elevation head. And also we have the work, either the work of the turbine or compressor. This part here, it could be the head, turbine head, or compressor head. And also we have some losses, which is denoted by HL, okay, HL, that's a loss, okay. So then if we go to Bernoulli equation, okay, so just let me adjust this a little bit better. Okay, Bernoulli equation in the absence of irreversibility, okay, the absence of irreversibility. And when, so in the absence of irreversibility, and when W dot CV for control volume is equal to 0. So when that is 0, we are going to have the Bernoulli equation, because in Bernoulli equation, you don't have the work of a turbine or compressor, okay? So then this is the straight line for Bernoulli equation, which is P1 over rho, since rho is 1 over V, or V equals 1 over rho, and this equation is simplified, okay? In general, the Bernoulli equation has this form, okay? In general, pressure plus 1/2 rho V squared, which we call it dynamics head or velocity head, plus gamma times Z, which is an elevation head, equal to some constant. But if we have an inlet and outlet flow, so we have the information on the left and information on the right, so we call it inlet and outlet flow rate or mass flow. Okay. So if we divide every term here by gamma, then we're going to see this formula here. Okay, so we divide that. So there we go. So that is something that you will be using in a problem-solving application. Okay. So I need to go over maybe an example problem so that see what's going on. Okay. All right. So example. All right. So just be patient. We will go through this. All right. So the substance we have is air. Okay. Air enters an insulated turbines. Okay. Insulated turbines. That means no heat transfer. Okay. No heat transfer. So when we have insulated turbine at the steady state at P1 equals 4.89 bar and T1 equals 607 degrees C and exists at 1 bar and exits, condition, and the inlet condition, exit condition at pressure of 1 bar, and temperature for exit is 570 Kelvin. So we have the inlet and outlet conditions for this turbine. We want to determine the work developed of air flowing through the turbine, okay, the work developed. and the rate of entropy produced, okay? The rate of entropy produced, which is sigma dot, okay? Sigma dot over m dot. And if you write the energy balance, okay, using the energy rate balance at a steady state for a control volume, and then adiabatic, this goes out, work or power for control volume, okay, for the control volume around this here, is equal to, or plus m dot, mass flow rate, change in enthalpy, and the kinetic energy and potential energy. So since we have V1, for example, is equal to V2, assuming that kinetic energy is very small compared to enthalpy, so the assumption indicates that this approximately zero and potential energy is zero because there is no elevation. Okay. So then we simplify this equation and we write it as the W dot CV m dot equals change in enthalpy. So we go to a table T9 and we get the enthalpy H1, which is 910.56, minus the enthalpy for temperature 2, which is 570 Kelvin. And then we get the work, or the work rate is 334.97 kilojoule per kilogram. Okay, so that's that. Now the interesting part is this. An entropy rate balance, okay? This is the energy balance formula, and this is the entropy rate balance formula, okay? So that is summation of Q dot over T, J is indicators, plus M dot times change in entropy, plus the rate of entropy production, okay? Sigma dot CV is the rate of entropy production. So if this goes to zero and I wanted to solve for and divide both sides by m dot, so then we have the rate of entropy production, sigma dot CV over m dot equals change in entropy. Now this is the, since we are dealing with the ideal gas, okay, since we are dealing with air, which is the ideal gas, okay, air entered an insulated turbine, then we're going to use the formula called the specific entropy that when we go to table T-9, okay, T-9, we can rewrite this as sigma dot CV m dot equals the difference of the specific entropy as a function of temperature minus, and because we have a pressure ratio, so we're going to use minus R natural log of P2 or P1 formulas, which is in the textbook. And it's just a universal type of formula, okay? Universal type of formula. So a rate of entropy production, that is called the rate of entropy production. And a specific entropy, this is denotes the specific entropy at temperature T and pressure 1 atmosphere. For air, we go to table T-9 and we get this information here as S2 minus S1, which is a specific, okay, a specific entropy, minus R bar, which is a gas constant, because R is equal to R bar over the molecular weight for air, which is 8.314 divided by 28.97, natural log of 1 over 4.89. Because the inlet or the outlet pressure is 1 bar and inlet pressure is 4.89. Okay, so the pressure decreases, okay? Pressure decreases. And when you go through this math, you end up with some approximately, you get zero, okay? Almost zero, okay? So you have a very small number and approximately, I'm sorry, this, I should just go a little bit higher here, okay? So when you do this analysis, you get the entropy production approximately zero. And that is the confirmation of second law of thermodynamics, okay? That confirms the second law of thermodynamics that requires that the entropy production be positive or zero. If sigma, which is the entropy production, is for irreversibility's presence within the system, okay? So irreversibility present within the system. And if sigma equals 0, that means no irreversibility. So we are in a borderline, okay? We are in a borderline, so it's approximately 0, so no irreversibility. So, but the key is it satisfies the requirements for the second law of thermodynamics for rate of or entropy production or rate of production, entropy production. So that is, and also I've assigned homework, okay? Assign homework that you will be utilizing this formula. And there are about a couple of problems on chapter 7, and I paid attention to give you problems to make sure that you, you have a good preparation for the exam number 2, which is Monday. I'll talk about the exam at the end of the lecture, okay? Just hang in there. This part here, any questions? This is really a fundamental formula for mechanical energy balance and also the entropy rate balance, okay? Entropy rate balance. And you can go to the book and there are a lot of information of explanation. So as a student, college student, you have to review the materials and your textbook and do some homework. And then when there's a lecture, it will reinforce your learning, okay? Reinforce your learning. And then when you take exam, that is the proof of the assessment that the professor tried to give you exam because they wanted to assess your knowledge, your understanding of the concept or the theory behind each topic, okay? So fantastic, okay? Fantastic. Let me just go to, let's see what I have in here, okay? I just don't want to repeat the same thing over and over. No, this is not a good idea, and I'm going to go over chapter 12, okay? Chapter 12, because I gave you homework on this chapter, so. All right, fluids mechanics and the momentum equation, okay? Momentum. In this chapter 12, you will become familiar about the fluid motion, internal flow, external flow, and surface and body forces, okay? Surface and body forces, viscosity, and the steady of compressible and incompressible flow models, okay? So, and also we're gonna just talk about the Bernoulli equation again and more details when we are dealing with fluid mechanics, okay? So the special part of Bernoulli equation said that if air is assumed to be incompressible flow, because the density doesn't change. Incompressible means density doesn't change. Compressibility means you have density of inlet and outlet will change because we're compressing air in a piston and cylinder, for example. Okay, all right, so, and Bernoulli said if the flow is incompressible, even if you're dealing with air, okay, air, under certain condition, okay, you cannot just say that air is incompressible. Air is a compressible substance, but we have case. If that case satisfied, then we say yes. We can assume that air is an ideal gas. It's not compressible. It's incompressible. Therefore, we can have a Bernoulli equation, which is the delta P equals 1/2 rho V square, and delta P is a difference between a stagnation pressure and a static pressure. Equals to 1/2 rho. Rho is a density, V square, velocity square, and that is called dynamic head. So the change in pressure equals dynamic head. They use this. There's a device called pitot tube. It was a French engineers that named after this French engineer by the name of pitot. So they call him pitot tube. They use that on aircraft to measure the velocity of air at high altitude. So the pitot tube sometimes at a very, very severe temperature, it may not function properly. So pitot tube still has been used in aviation, so that there was a crash. One of the plane crashed a while ago, and then they found out the reason this plane crashed because of the pitot tube reading that was incorrect reading. It was not measuring the air velocity correctly. So because if you have the air velocity, then the change in pressure, because when you have at the point of pitot tube, there is a point, we call it the stagnation point, where the pressure is higher, but the flow come to rest. When the flow come to rest, we call that point of a stagnation point. And then we have a static pressure a little bit further away. So just wanted to, because I did the research in that area, so that's why I'm more like, I'm excited about the Bernoulli equation, because I did the papers on that, okay, also. Application of Newton and second law, okay? Application of Newton and second law to obtain the momentum equation for fluid flowing through control volume, okay? I'm assuming that all of you have taken dynamics, okay? Because I used to teach dynamics at USD and also Mesa College for 14 consecutive years. And we have a topic called fluid flow or steady flow of a stream of air or substance going through the, sorry about that. Let me just turn off my phone. Through the, pipe. So in dynamics, we had to drive the formula for momentum, or linear momentum, we call it, so that we have a linear momentum versus angular momentum. So the angular momentum is the moment of a momentum, we call it angular momentum. So that is the dynamics course that there was a chapter about the flow or fluid flow. Okay, so the application of Newton's second law to obtain the momentum equation for fluid flowing through the control volume. And if we have a surface here, or the area, and we have a pressure or normal force, and we have a shear force, okay? Shear force is tangential to the surface, and then this force is a normal to the surface, okay? Normal to the surface. We know by definition that pressure is in Pascal, which is the normal force over area. We call it, normal force over area, which is Newton per meter square. We have also terminology in material science, we call it a stress. A stress is also force per unit area, which has a unit of Pascal as well, okay? A stress. And the shear force, so the shear force is denoted by this symbol, tau, we call it tau, shear force. And the shear, we call it also shear stress, okay? That's the shear stress. And this is the shear force is equals to shear stress times area. Also, this is the shear force is known as tangential force versus normal force, okay? Tangential force, and that is tau, maybe we call it T, correct? Tangential or shear force, and also we have the shear stress times area. This is equal to force, shear force. Okay, maybe I'm going to just do that. Okay, shear force. There we go. Let me adjust my papers in here and try to explain this part here. Okay, all right. So very interesting. Because in the fluid flow, not always the diameter is uniform throughout the pipe. Sometimes the pipe is going to have a decrease in area, and then the pressure will increase and velocity will increase, okay, at the inlet, like a nozzles, okay, nozzle. So in the form of, say, we have a device that flow goes into it, and then you have a sudden of contraction or change in the area. So, and there is a force exerted on this side, which is a P1A1, and then we have a force in opposite direction, reaction, which is a P2A2, and also we have a for the control volume, we have an atmospheric pressure, which is the change in area, okay? Area 1, area 2. Okay, Put your seatbelt on. Remember, in a static class, we had summation of forces in x direction equals FRX, which is the resultant force. Okay, so P1 in this direction, that's a frame of reference. X is positive, Y direction is positive. So we have P1A1 minus P2A2, and then minus P atmospheric ATM, I call it. Okay, P ATM, atmospheric pressure, times the change in area. So if you simplify this summation of forces in x direction, P1 minus, P at ATM times A1, let's say simplifying this for this equation, minus P2 minus P ATM times A2. We know that P1 minus P atmospheric pressure and P2 minus P atmospheric pressure are recognized as the gauge pressure. Remember, the total pressure is always equal to gauge pressure plus atmospheric pressure. Okay, so here we have P1, which is the total pressure, minus atmospheric pressure. We call it the gauge pressure. So that's a gauge pressure. And then if we say summation of forces in x direction is a P1, substitute this by gauge pressure times A1 minus P2, because you can measure the gauge pressure. Okay, you can measure from the dial indicators, okay? Gauge indicators. So, and then we have this formula here for the summation of force, because there is no forces in y direction. So summation of forces in y direction is 0 for this example. Then we have a velocity profile also, or if we wanted to determine the shear stress, it's a very popular formulas in fluid dynamics. Okay, in fluid dynamics, we have this viscosity, mu denotes for viscosity, shear stress equal proportional to dynamics viscosity. We call this viscosity, or it's known as dynamic viscosity, times the velocity gradient. That's a velocity gradient. It's a du or d velocity dv or du over dy. Okay, it depends on how the notation is. So if you look at this, that's a profile, the velocity profile in terms of shear stress tau on the surface. We have the velocity gradients. We have the dynamics viscosity. So the product of these two, we call it the shear stress. Little v, if you see the little v, that is, again, is not a specific volume. In thermodynamics, we call it a specific volume. In fluid dynamics, we call it kinematic viscosity, okay? Kinematic viscosity versus dynamics viscosity. The ratio of dynamic viscosity over density of that fluid, we call it kinematic viscosity. So that is a useful formula, okay? All right, so, any questions? I think this is easy to understand, okay? The concept of fluid flow. Incompressible flow, okay? Chapter 12, density or kinematic viscosity of liquid, okay? Density or, again, we have to be careful whether the V, low V we are using is a specific volume or velocity or kinematic viscosity, okay? So someone, when they design the problem, you should just say, you should state that whether this is, you're talking about the kinematic viscosity or you're talking about a specific volume, or you're saying this is a velocity, okay? All right, so of liquids varies low with pressure at fixed temperature. These two properties, maybe I can see that is not a kinematic viscosity, okay? That's a rho, this is the specific volume, because those are the, because rho and V, they have inverse relationship, okay? Inverse relationship. All right, so the density of air and other gases can vary significantly. The density of air and other gases can vary significantly. Flowing air can often model as incompressible, okay? Just pay attention to this part here. when trying to prove the Bernoulli, okay, law or Bernoulli equation. When the air is flowing, can often model as incompressible, provided that the velocity of air is not too great, is not too high or not too great, and temperature is nearly constant. As a rule of thumb, okay, velocity of air less than 100 meters per second or 330 feet per second or 225 miles per hour can be modeled as incompressible flow, okay? Although air is compressible, but if this condition is met, then we can assume that the flow of air is going to be considered as incompressible flow, okay? That's the key, incompressible flow under this condition here. At higher velocities, density change becomes important. Then compressible flow principle apply, okay? Because for incompressible flow, such as water or air at a low velocity and nearly constant temperature, we consider that to be incompressible flow. When we say incompressible, that means the density doesn't change, but it's a compressible fluid, the density changes. Okay. So then we're going to go over okay, that's the proof for the, if you can, in a Bernoulli condition or principle, stated that air is considered to be incompressible fluid, because they're assuming that the velocity of air is not too high. Momentum equation, Newton's second law. Newton's second law says force equals mass times acceleration. And then acceleration is the instantaneous rate of change of velocity with respect to time. So acceleration is dv dt. So if you rearrange this, okay, or cross multiply, so then also the A is going to be, we're going to substitute in the second law, A equals dv over dt. And then if we just say mv or dmv, okay, that's a department of motor vehicles, so we always memorize that, the dmv, okay? dmv with respect to time, that dmv is known as linear momentum. But if we can also say that this is with respect to time, so we have a time rate of momentum transfer, m dot v, that's a velocity, okay? Okay, so just kind of, I wish they would use different, nomenclature. So that's a velocity, m dot v equals time rate of momentum transfer into or out of the control volume. Therefore, the momentum equation is going to be written as such, okay, from the second law of thermodynamics, the second law of Newton's second law. So the force equals the time rate of momentum transfer out minus the inlet time rate of momentum transfer into a control volume. So that is a very useful formula. We call it the momentum equation in fluid mechanics. So it's good to know that when you go to higher level courses in thermosciences, and then you can say, yeah, I have, learn about the momentum equation using the Newton's second law, and I know about the Bernoulli equation. I know what the condition for compressibility and incompressibility. So that is something is going to help you down the road as you take more courses, okay? All right, so the Bernoulli equation, again, we're gonna revisit the Bernoulli equation. Pressure plus 1/2 rho v squared plus gamma times z equals some constant along a streamline, okay? Gamma z is z times z, which is the elevation, is hydrostatic pressure, okay? The note for gamma z, or they call it elevation head. That's a hydrostatic pressure. P is a static pressure. 1/2 rho v squared, we call it dynamic pressure using a pitot tube, okay? That's how you spell the pitot. That's a very nice, it looks like this. That's a L-shaped type of device. And It has a cylindrical, and it has a port in here, which we can connect that to YouTube manometer assembly. So we can just have an incline manometer assembly that is in the laboratory setting. You can also calculate it. You can determine the difference in pressure, which is a stagnation pressure. That's a stagnation point. At that point, the velocity is 0. And when we have a pipe or conduit or a round pipe or square pipe, we'll insert the P2 tube. There's a hole in here. You insert in there, and then this will be perpendicular to the flow that is coming toward it. Okay, and then when you have this air velocity, inlet velocity, and that's a velocity profile, and we have a point which we call it a static point, and V equals V1 at that point. Okay, if that's the point of V, we call it V equals V1, and this is a V2 equals 0. Or if I could call this point somewhere, there is a little holes around this periphery of this pitot tube, and that is measure the static pressure. Okay, measure the static pressure, and then the stagnation pressure is at the nose of this pitot tube. Okay, so if you have never heard this, this is the first time, but that's what this is. Okay, it was named after a French engineer, so by the name of Pitot. Okay, maybe we're not pronouncing it correctly, but the people call it Pitot tube. Okay, Pitot tube. But nowadays, I have used this in the laboratory sitting at San Diego State for 5 years. I taught the thermofluid and heat transfer lab, and we had the experiment called measuring the 3 basic fan laws. So we had a blower with a certain RPM. The flow was going through this air duct, and then we had 2 types of measuring devices. One we called it the technology device. Nowadays device, we call it a vane anemometer. So the vane anemometer will measure the velocity directly, but the pitot tube has to be connected to the YouTube inclined YouTube manometers, and that will give us the change in pressure. The change in pressure means difference between the stagnation and the static pressure will give us the dynamic head. The dynamic head is 1/2 rho V square, velocity square. So the vane anemometer gives you the direct velocity, so you can find the difference of the 2 pressure. But if you use the pitot tube, we can use the delta P information from the YouTube manometer, and we solve for velocity. So the students in the lab were comparing the 2 different devices to see if it will satisfy the Bernoulli equations. Okay, all right. And the velocity of air was not too high, so we consider the density to be constant, or it doesn't change. Okay, that's why the Bernoulli equation is going to say delta P is equals 1/2 rho V squared. All right, great. So that's what we have, and we know that this is a pressure head, that's a velocity head, that's a head loss due to friction. And then if you go over the mechanical energy equation, which we have already discussed this here, and then if we had the power, which is the W dot CV over M dot, it could be the power of a turbine and minus the power of the pump, and then the head for the pump is written as such, or the W dot P for the pump is over gamma times Q. Q is the volume flow rate. Okay, volume flow rate. And then for the turbine is this here. Okay, the same thing. And instead of P, we have a T for turbine. And head loss must be greater than 0. And then the head loss of a pump is greater than or equal to 0. And the head loss of the turbine is greater than or equal to 0. Okay, all right. So that is what we have. Let me just go over example for the Bernoulli equation here. Okay, just hang in there. Let me see what I have. So fluid flow Bernoulli equation. So we have a pipe, okay, with different elevation, okay? Elevation 1, with respect to some point or datum here, we have a H1 of 5 meters, and then at that point, point 2, we have an elevation of 10 meters. And the flow, it has the same velocity, okay? The flow going through this here pipe, it has the same velocity, inlet velocity and exit velocity are the same. And we have the inlet pressure of 2 atmosphere, okay? And 1 atmosphere is equal to 1.013 times 10 to the 5 Newton per meter square Pascal. So 2 atmosphere is 2 times that. So we wanted to, if we know the inlet pressure, we don't know the outlet pressure P2. So we wanted to determine that using the energy balance or Bernoulli equations, okay? Bernoulli equation. So here, since the velocity is not that great, okay, it's not that high, so this term, the velocity head, or 1/2 rho v square, is constant on both sides, and the density is also constant. So therefore, this term and this term will cancel each other out. And then we have, if the elevation goes up, so the pressure goes down, okay? As the elevation goes up, the pressure, the exit pressure will go down. And we're gonna check on that, okay? All right, so, and then we have a P2, we wanna solve this for pressure, exit pressure, which is P1 plus rho G times the change in head or elevation. This is not enthalpy, okay? We can just say maybe this is Z1 and this is Z2, okay? So that we don't get confused between the enthalpy and elevation, okay? So then we have pressure is 2 atm, and then density of water, we all know that is a 1,000 kilogram per cubic meters, the density of water. Okay, so again, the fluid is water, okay? But you have to be careful whether it's air or water. Okay, so this is a density of water times the G. G is a gravitational acceleration, 9.81 meter per second square. And the change in elevation is 5 minus 10. So you do a little bit of math. So we end up with 2 atm here. And all this is gonna give us minus 49,000 Newton per meter square here. Okay, this part here is gonna give us 49,000. But we know that we want to convert this to ATM, okay? ATM means atmospheric pressure. So Newton per meter square, 1 ATM is 101,300 Newton per meter square. So the Newton per meter square cancels. So this divided by this number gives us 0.48. So 0.48 ATM, now we have the same unit, ATM. Therefore, the exit pressure is 1.52. So you can see that the pressure, inlet pressure was 2 atm, and then the exit pressure ended up to be lower since the elevation increased and pressure decreases, okay? So this is one. I think that's good enough, okay? And that's good enough, and because I have to talk about the other stuff. So this is just in a nutshell, this is the bulk of chapters 7 and 12. And I gave you homework for chapters 7 and 12. Please work on it. And I don't want to put pressure on you to finish it by Sunday, but try your best to finish that by Sunday. And so if you work on the homework, then you will be ready for exam. So far, okay. All right, very good. Exam. It's going to cover, okay? I'm going to just let you know the topics that will be on the exam. Chapter 5, okay? Chapter 5 will be the, that you did the homework on chapter 5. That will be on the test, problems from that chapter. Chapter 6 as well, okay? Chapter 6 and chapter 7. I'm trying to cut down on number of chapters. So chapter 12 is not going to be in this exam yet, okay? Not going to be in this exam number 2, but it will be on the final exam. So we're going to talk about the final exam on Tuesday, okay? Final exam, we're going to talk about it on Tuesday, next Tuesday. So the 3 chapters, 5, 6, and 7 will be problems from those 3 chapters will be on the second exam. Now, second exam procedures or rubrics will be the same as the first exam. And let's see that again, the timing, okay? The timing. I would like you to just have a folder instead of the, the share folder, just to email it, email it to my Google email address. Because when I get that in front of me on my screen, I can just click on it and then I can see the problems one after another, okay? So I don't have to go to the drive or type your name on a shared drive. And some of you, I could not really, at least one of the students, I typed the name of that student, it did not really came up. It says it's empty. It says empty share. So that's another thing. So to minimize that kind of headaches, please submit your exam. Remember, 1 or 2 students, I will say at 1 student, okay, did not follow the rules or the procedures for submitting the exams. 1 submitted the JPEG picture. Please convert that to PDF and don't send me page by page by page by page like 10 pages. Just combine PDF. It's very easy. If you don't know how to do it, just go to Google and then say, how can I combine them, or convert it from the JPEG to, all the computers will do that for you, to PDF file, and then combine all the pages, okay? Have a file. I'm just repeating that because 1 or 2 may not follow that. That took me 10, 15 minutes extra time trying to figure out what's going on, and it was really, really frustrating. Okay, all right, so I'm not going to say the name of that person. Probably that person knows what I'm talking about, without telling the whole class who that person is. But please, if you are the one, try to convert your picture that you took, like the way I did it, correct? I learned how to do that, correct? I just took pictures and then I converted to PDF and then I posted on, and then I created a folder in my desktop and then I posted on Blackboard. I think it looked good, correct? It was good. So let me get out of this part here. Okay, let me just see if I go and all right, so beautiful here. Okay, great. Oh boy, what a day. Okay, what a day. All right. Let's see what else I wanted to clarify for the exam. Okay. Exam, I'm going to, because number of you are in overseas, so I'm going to do the same thing as the first exam. Okay. I'm going to post it by midnight Sunday night. And then you have until Monday, before 10 p.m. You can just, if you finish it earlier, just please do not put it on a shared drive, okay? Just email it so I can see it directly that you emailed me exam, okay? Then I can write your name down on a sheet of paper. I said this student submitted the exam, so I can write it down. And then 1 student or 2 submitted the exam, but it says blank. It was blank. And then you had the exam sheet, and then you submitted that, and then it was blank. There was nothing on it. Okay, so please pay attention when you're submitting your work. Okay, all right. So I wanted to just learn from the mistakes and then not to make the same mistake. Okay, all right. So any questions? Okay. So exam will be posted on Sunday. I don't know how many questions at this point. You might ask me how many questions. I really don't know at this point. I'm going to design the exam and you will find out. Okay, all right. So by now you should be very comfortable with what we have covered so far. And then one more topic I have to cover. I mean the remainder of chapter 12 or fluid dynamics and heat transfer, okay? The heat transfer conduction, convection, radiation, which is required for this course. To complete this course, we need to go over 3 modes of heat transfer: conduction, convection, and radiation. Okay, so then I'll tell you all about the final exam, what will be included in the final exam. So, any questions? And I have the number of, let me just stop the